All right, that's the first point. IID stands for independently and identically distributed, within which you check whether the errors are normally distributed or not. That is called as normality assumption. Second thing is errors should be having zero mean. The third thing is that errors should have constant variance. What if your errors do not have a constant variance? What do you call that problem as? If errors have constant variance, you call that as homoscedasticity. What if errors do not have constant variance? What do you call that as? Heteroscedasticity. Absolutely right. What is another name for heteroscedasticity? What is another name for heteroscedasticity? Or what is another name for homoscedasticity? Heterogeneity. Absolutely right. No, autocorrelation is different, Aditya. Autocorrelation is different. Now, yeah, there is a fourth one which is coming up, which is independent of each other. So your errors should be independent of each other. Right? This also means that their pairwise covariances are zero. We refer this particular assumption of error as independent errors assumption. The name itself says, right? So it's independent errors assumption. What if this assumption does not hold good? If this assumption is violated, what do you call that problem as? Anyone? Aditya, you have already told that. It is called as autocorrelation. Right? If this assumption is violated, you call this as autocorrelation. If this assumption is violated, it is called as heteroscedasticity. Right? There is another error which is coming up. I want you guys to let me know what that error is. So here we go. Assumptions about the predictors. So we have the linearity assumption wherein all of your inputs are assumed to be linear in the regression parameters. So you have beta naught, beta 1 in all this, right? These are called as regression parameters or coefficients. So the y should be related to all your inputs linearly with or after using these coefficients. That is what it means. Linear in parameters means your y or the relationship between y and x is linear given these coefficients. That is why, or given these parameters. That is why it is called as linear in parameters. So, and then we have assumptions about the errors, we have assumptions about the predictors. And what was the first assumption? All your predictor values should be non-random. That means you should have upfront identified all the observations of input variables. Say there is one input variable called x1, your x11, x12, x13, so on and so forth, right? Say x1 is height of people, right? It's height. So this is height of first person, second person, third person, so on and so forth. All these values should be upfront fixed or should be selected in advance, right? It should it is clear that under non-experimental or observational situation, this assumption will not be satisfied. So if it's just observational situation, randomly you pick up some number, randomly you pick up the heights. If you're going to pick the values in that way, the assumption that the values should be non-random is obviously violated. important, right? So you upfront take the heights of the people. Based on that, you build a model. That is nothing but you base your model on the historical data. Next thing is that your values, whatever value you take, say you're taking or measuring the heights of the people, height of first person, second person, so on and so forth until height of nth person. Can you be 100% accurate with the measurements that you're taking? If I give you a tape to take the measurements, to measure the heights of the people, will you be accurate 100% of the times? That is my question. No, obviously, right? There will be some amount of error always. Hence, this particular assumption is hardly ever satisfied. I would say it's never satisfied for that case. No matter how sophisticated equipment you use, right? Satisfying this assumption would be a key challenge. And the next thing is linearly independent of each other. What does that mean? Your input variables are assumed to be linearly independent of each other. What if this assumption is violated? What do you call this as? What do you call this if this assumption is violated? No, already autocorrelation is done, right? If your errors should be independent of each other. If your errors are not independent to each other, you call it as autocorrelation. If your predictors are input variables, absolutely, you got it right, Vijay. So if your predictors are linearly independent of each other, you call this as collinearity. I'm doing a recap once again because this is extremely important. And we have the final assumption about the observations. All observations are equally reliable. You're relying on each and every observation, each and every height that you take, right? Measurement, height of the first person, second person, so on and so forth, right? Each observation is equally reliable. You can rely on the data, and they have an approximately equal role in determining your output, right? And each of these are equally responsible for drawing conclusions out of your model. That is what this last assumption means. Simply speaking, I rely on each and every data point. Okay, remember this line: linear, independent, normal, and equal variance. So all these parameters should be satisfied for you to say that, all right, I can proceed with my model. For you to just make that statement, you look into all these things. Now, let us proceed with this. Here, we want to measure the sales or the consumption of cigarette. And for consumption of cigarette, which is Y or sales, you have all these input variables or X's. Can someone say which of these inputs are significant? Which of these inputs are significant? Sorry about that. I was just trying to get rid of something from my screen. Okay. Anyone? Which of these inputs is significant? Right, Ramanand, it's price. Why is that so? We look into the values which are towards the left of 0.05, and in this case we have 2 stars here. That means price is significant. And there is one more place where we have a small dot. Dot is to the right of 0.05. That means it's not, I mean, you can probably consider that as significant, right? So let us say this is also significant, though it is towards the right of 0.05. Since there is only minute difference between these two, you may want to consider that. You might want. And if I look into the R squared value, what's happening here? Yesterday I've explained you about the difference between R squared value and adjusted R squared value, right? If you add new variables, say you have age, high school income, black, female, and price. What if I add something called as location of the person, right? Location, where he is stationed as of now, where is he living, right? If I consider location of a person, if I'm going to add this variable, inclusion of this variable might increase, might, M-I-G-S-T, might increase the multiple R squared value. So the addition of new input variables might increase my multiple R squared value, or removal of input variables. For example, if I remove price and female from the data set, removal of these data point or variables might reduce the R squared value. So your R squared value tends to change based on addition or deletion of variables, irrespective of whether those variables are impacting your outcome or not. Irrespective of that, it's going to increase or decrease. Hence, we look into adjusted R squared value. One more thing, 32.08 or 32% here says that 32% of the variation in your Y, which is sales in this case, so 32% of the variation in sales is explained using these input variables. That is the statistical inference. That is the statistical way of mentioning things. However, the same explanation does not hold good for your R squared, adjusted R squared value. You cannot infer in that way, right? How do we infer? No, there is no kind of straightforward way of inferring things here. All right. One more thing, if you notice here, higher the t value, lower will be your p value, right? Higher your t value, mod of t, lower will be your p value. Just remember that. So in this case, if I take mod of that, it's higher, right? Higher the t value, low will be your p value. Again, you need to look into your t-test, which we have already done, and try to figure out that. And this t-test is used for each and every individual, right? Each and every parameter or coefficient, beta naught, beta 1, so on and so forth. However, for the entire model, we use something called as F statistic. F statistic, right? Here also, higher the F value, better it is for you, because higher the F value, lower will be your P value, right? This P value is for your overall model, and these P values here are for your individual input values, individual input variables. Okay, what do you mean if P value? All right, you're always saying that if P value is less than 0.05, it's significant. But what does that really mean in this scenario? It means that the coefficient here is significantly different than 0. What does that mean? If P value is less than 0.05, it in reality means that the value which is presented here is significantly different than 0. That is what it means. And if I have a 0 here, for example, if I'm going to multiply 0 with price, price will become 0. So this entire variable is gone, not required for me. If I get a 0 here, coefficient female. If I multiply 0 with any value of female, I'm going to get 0. Hence this female variable is insignificant. When do you call that it is significant? When p-value is less than 0.05, which in reality means that the coefficient value is significantly different than 0. And there is less than 5% chance of you going wrong. Remember once again 95% confidence interval. 95% confidence. What does that mean? 95% of the times the decisions that you take should be right. I give you an opportunity to go wrong only 5% of the times. So when I say p-value is less than 0.05, that means I'm saying that probability of you going wrong, if it is less than 5%, that means the decision that you're taking is apt, right? Okay, and remember, higher the t-value, lower will be your p-value. Higher the f-value, lower will be your p-value, right? F statistic and p-value associated with that is for the entire model, right? And here each p-value is for a different x. Is this clear, or guys, do you have any doubts here? Also, lower the standard error, better it is for you. Okay, it's clear for Vijay. Everyone, I want response from everyone, please. Aditya, it's clear for you. It's clear for Rajiv. Ramanan, is this clear for you? Yep. All right. Perfect. So let me take this form. ANOVA table. I'm not going to spend a lot of time on this because already we have spent sufficient time on this, right? ANOVA. Go back to the first few sessions and you'll see the recording on ANOVA exclusively, and how to calculate sum of square errors, mean sum of square errors, f value, and all that is mentioned there. Oh, I think these things we have discussed yesterday itself, right? Sorry, these things we have discussed yesterday itself. I think we have discussed until partial correlation coefficient. Now we have this Anscombe's data, which is considered to be uh, very important for explaining you on why graphical representation is equally important. So look at this. We have X and Y here, and this is your dataset 1, and here you have dataset 2, dataset 3, and then you have dataset 4. So you have 4 datasets. The number of data points used in each and every dataset is 11. So you have 11 data points across your datasets, 11. And if you look into the mean value is approximately the same across. Standard deviation is the same across. Correlation coefficient, R, is the same across. What does that mean? 0.82. Does this mean 0.82? Does that mean that the relationship between X and Y would be in this direction? Agree, everyone? Positive correlation coefficient, what does that mean? Yeah, Aditya, you agree with me? Remember, or did you guys forget? R value is called as correlation coefficient. If this value ranges from -1 to +1, closer the value to the +1, more is the strength of the relationship. Yeah, positive direction, absolutely, Raman. Right, Aditya. Now let me show you the graphs of each and every data set. You'll be surprised now. Look at that. Though we were expecting the data points to have a positive relationship and strong positive, here it doesn't seem to be that positive. Here also it's okay, but there is an outlier. And here it's curvilinear. And here it's a different data set altogether. Data points are vertical, not horizontal. And here you have one data point. Hence, just based on your statistical values, you cannot comment about the data. Instead, you need to plot that. You need to do a scatter plot to necessarily look into the relationship. Only then you can conclude whether the relationship is linear or not. Here we also have placed cards.txt. There is a data set. I'll be sharing everything across if I haven't done so. We want to build a model to predict miles per gallon of a car based on the volume, that is cubic capacity, based on your horsepower, based on your speed, and based on the weight of the vehicle. Right? This is the data set. Okay, so let me move on. Here is a scatter plot matrix which has all the values. Now look at this for some time and let me know what are your key inferences. What will be your key inferences on what two variables have good relationship, positive, negative, and things like that. Just spend some time here. Yeah, I'm awaiting a response from your end. Look at the scatter plot and comment, please. Assume that there's your diagonal there. Unable to infer anything? Let us look into this. What is the relationship between HP and miles per gallon? Seems like it's a negative correlation. Yeah, right. Right, Aditya. So Aditya says HP and SP, there is a strong positive relationship. Here we have horsepower and here we have your SP. By the way, what SP stands for? Okay, top speed, sorry. Top speed and horsepower, the relationship between these two variables is strong. Right. Also, the relationship between horsepower and miles per gallon is negative. There's a negative correlation and you can see the corresponding negative value also here. So that is your R value, small r, correlation coefficient. And let us see what is the correlation coefficient value for HP and SP. It's 0.97 there. There's a high correlation between these two variables. And there's absolutely perfect correlation between volume and weight. It's 1. And you can make out the correlation between two variables by looking into this one. So this also seems to be negative correlation between miles per gallon and top speed there. It's minus 0.67, right? And anything else which seems to be significant, nothing else. So first, by looking into your scatter plot and the correlation, you get to know what is the relationship among the various variables. Okay. So you have seen the scatter plot diagram and the regression output also. Do you see something unexpected in the regression output here in comparison to your scatter plot? If yes, what is that? Anyone? No one has seen anything unexpected here from the scatter plot and the regression output here? Okay. We do not have a lot of time at our disposal to waste, right? So volume and weight have perfect correlation, both volume and weight, these variables, right? And you have the corresponding small r value, which is 1. However, if you see here, both volume and weight are insignificant. You do not have any stars right there. So both are insignificant and all the other things are significant. So this is something which is unexpected here. Our residual standard error is low. We have the adjusted R squared value there and the p value is very low. That means our overall model is also good, right? And higher the f value, lower will be our p value. Here it will be n minus 1 because the number of variables minus 1 would give you 4. And I think it's n minus p minus 1. That is how the number of observations. Okay. Anyways, so now if we just do miles per gallon on weight, I'm taking only this one input to come up with a simple linear regression. When I use only volume, this seems to be significant for me now. If I do it with only weight, even weight is significant for me now. Though the R squared value is pretty low because there is only one value, and p-value overall model is less than 0.05, so overall model is also significant. Now I have two things. So what do I do now? Let me consider both of these and then try to build the model. If I consider both of these, the R squared value has further dipped, adjusted R squared. I'm looking into adjusted R squared because I'm removing few variables, adding few variables and testing, right? Hence my focus would be on adjusted R squared. Here both of these do not seem to be significant. In such scenarios, there seems to be a problem here. It seems like there is a problem here. So what do we do when we have a problem in this way? We actually proceed to do deletion diagnostics. We want to identify whether any particular value is doing these kind of, what do you call, um, weird activities to our regression model. Is any one value is influencing to a great extent the model or not? We want to find out now because it's very strange. If I use volume and weight with other variables, except for volume and weight, everything seems to be significant. However, if I do regression only on volume, it's significant. Only on weight, it's significant. But if I use these two, there seems to be a problem. So I'm not sure whether this is a problem with collinearity or not. So what do? I resort to deletion diagnostics and influential observations, right? What are my influential observations I need to identify? You all know what is residual, right? You all know what is residual? What is residual? What is another name for residual? Error, right? Error or residual. You all know how to calculate that. That is nothing but the difference between your actual minus your predicted. And predicted values represented hat, using hat, y hat. There is also something called as standardized residuals. All you do is you divide your this raw residual by its standard deviation. How do you standardize? Normally it's x minus mu by standard deviation, right? Z value. So on similar lines, if you were to standardize this, we are going to divide your normal residual by standard deviation, and then you get standardized residual. However, you'll not come to know the population variance. So residual standardization, right, or standardized residuals is usually not a practical calculation. Hence, there is another variant to this residual called as studentized residual. And this studentized residual is once again the raw residual divided by your standard deviation only, but this time the standard deviation would be estimated standard deviation. That's it. You divide your residual by standard deviation to get standardized residual. However, you will never come to know about variance value or standard deviation, right? Square root of that would be standard deviation. So you'll never come to know about the standard deviation of the population. Hence, you estimate your standard deviation and then divide it. And that is called a studentized residual. Then you have hat matrix diagonals. Just remember that hat is nothing but your predicted values, right? And that as a matrix. Using that matrix also you can identify what is your influential variable, but we'll not spend a lot of time on that. However, we're going to spend a lot of time on DF betas and DFFITS, right? Difference in betas and difference in your fits. Difference in your betas means you have beta naught, beta 1, beta 2, so on and so forth, right? So what you do in this case is I first calculate all these coefficients or parameters or beta values before deleting any variable or any observation. What does that mean? So say you have volume or weight of vehicles, right? So this weight is called as a variable, right? So what I do is in DF betas, I calculate beta naught, beta 1, beta 2 and all that even before deleting anything, any variable. I consider all my variables, all my observations and calculate the betas. The next time I try to delete few of the variables, one variable or one observation, and then once again I'm going to calculate beta naught, beta 1, beta 2, so on and so forth. I look into the differences of these betas. That is called as DF betas, and you have DF fits, right? What do you mean by fit? It's a difference in fits. Fits is nothing but your fit model, right? Your predictors basically. And then Cook's distance, we are going to spend some time around that. So don't worry at this point of time. There you go. So you have DF fits, difference in fits. By looking at this index plot, it's extremely clear for me that observation number 77 seems like an outlier. What do you guys feel? Do you see that there is any other value which is significant here? Right? So what is DFITS? DFITS, right, is the difference between The absolutely, yeah. What do you mean by fitted value? Fitted value is nothing but your output only, right? Predicted value. So this is nothing but difference between the ith fitted value, and this is obtained from using your full data. You're not deleting anything at all, absolutely. And if you subtract this with another fitted value, it's called as yi of I. If we subtract these two, right, and then of course there are a few more calculations which are required apart from that. You divide it by standard deviation, fitted value, and there is something called as PII and all that. So I'm not trying to confuse you here. So if you subtract those two, then you get the difference of the fitted values, right? And here, forget about the calculations. Your R or SAS or SPSS or MATLAB or Stata or Vector or whatever, Minitab, whatever tool you're using is going to calculate these things for you. Only be concerned about the interpretation. If you have any extreme values like this, you say that this is the influential value in my data set. And there is a thumb rule, right? P2 square root of p plus 1 multiplied by n minus p minus 1, right? All your p are your x's. How many x's you have? x1, x2 until xp. And n is nothing but the number of observations within this one, x11, x12 until x1n. So anyways, do not worry about this. No one is going to stick to this, or it's p plus 1 divided by n minus p minus 1. So if your DFFITS value is greater than this value, you call that value as influential data point. But no one is going to stick to this, right? That is just a thumb rule. No one will stick to that. If you instead see some points which are significantly or abnormally different from the rest of the data points, either using this index plot or using your dot plot or using your box plot, right? That means this is your influential value that is actually influencing the entire model. Your entire model, prediction model, is influenced by one value. We don't want that, right? We want our model to be generic. We want a prediction to be generic. We want our prediction model to predict for all the values equally well. We don't want our equation or prediction to be biased just because of one data point. Say you have heights of people. There's one person who has a height of 8 feet. Say that is your influential variable using this index plot. What does that mean? That means that there is only one value which is defining your prediction equation. Do you want your prediction equation to be built in that way, wherein one value is significantly influencing your model? No. We want all these values to equally contribute to your prediction equation. Hence, probably we need to delete that. But there has to be a lot of analysis which has to go behind the screens even before you delete even a single value from the data set. So that's okay. Now we have something called as Cook's distance. All these measures, right, diagnostic plots, are going to help you achieve only one objective. The influence of an observation, right? Even before I make a statement, let me tell you this. The influence of an observation may be measured by the effects it produces on the fit or on your model when it is omitted from the data. If you omit your data called 77, what is the kind of influence it is going to have on your overall model? That is what we are trying to come up with here. And there are multiple different measures used to check on which variable is influential. One such measure is called as your Cook's distance. This also measures the difference between the regression coefficients which are obtained from your full data and the regression coefficients obtained by deleting the ith observation. It's similar to the difference between your fitted value obtained from the full data and the fitted value obtained by deleting the ith observation. Similar to the previous plot which we have seen, this plot also works. But remember one thing, that if you have any abnormal value, once again, that means that is influential. You delete that and check on how your model is behaving basically. And here also there is a formula called CI, Cook's distance value, right? Again, I'm not getting into the calculations of that, but remember that if the CA values are greater than 50%, or 50% point, basically greater than 0.5 of the F distribution, then you call that as influential. Or in practical scenarios, if the CA value is greater than 1, so if you look into that, this value is close to 1, it's not 1, right? So if the CA value is greater than 1, you call that as influential value. But we once again don't go by all these calculations. We just look into this graphical representation, and if we see any value which is abnormal or which is standing out from the rest, that is when we flag that value and say that 77 is influential observation. So you can also look into all these plots and check which value is is shown as significant. There you have 77. On similar lines, you also have studentized value, studentized residual, which we have discussed, right? That also is showing that 77 is a significant value. And you have Bonferroni p-value. Think about this as one of your hypothesis tests, right? And here also, if the p-value is less than 0.05, then that means it's significant basically. So 77 seems to be significant because it's less than 0.05, I believe, or it's very low there. And even if you look into your hat values are nothing but your predicted values. I feel that 77 is significant, also 71 and 81 to some extent. However, in Bonferroni, 71 and 81 does not seem to be significant. Only 71 is significant across, and also 71 to some extent here and here and here. So let us delete this value variable 77 and see what happens to our regression model. If I delete the 77th observation, I do not see any significant difference there. But when I delete that and plot my diagnostic plot, I feel that 79 is another variable which comes up now as being significant. Now let me delete also the 79th value. But if you notice, when I delete the 79th observation, your intercept is becoming significant. Is becoming insignificant there. So it's making a huge difference, right? And even if you look into your R squared value, where is that gone? Yeah, this is with your deletion of 77th value. I look into my adjusted R squared value. If I look into here, it's changing. So it's improving my model basically. And once again, after deleting, if I look into my diagnostic plots, 80 turns out to be the most significant, most influential value. But that doesn't mean you keep on deleting the data points, right? If you delete one data point, another might appear as influential. So you actually do not delete without any prior understanding of the data, right? So you analyze thoroughly to your heart's content before deleting any value. Your business knowledge is required. First of all, you check whether that value is a data entry. Does that value appear there because of a data entry, right? And outliers or these influential observations should not be deleted. It's a bad situation. We should not be doing that. In fact, right, if you analyze, if you feel that that is a correct data point, say you have measured the height of a person as 8 feet, say that is a right data point, you have measured, taken right measurement. In such scenarios, probably that point is extremely informative point, right? So those kind of things are extremely important. Take an example of bacteria. What happens to bacteria? Bacteria in the initial stages, it will be low like that. All of a sudden it's going to burst out. That is that is very informative for you, right? To know on when the bacteria is exploding like crazy. Just because that's influential observation doesn't mean you delete that and ensure that your model fits in well. Okay. Now